the next few slides is theory. You can appreciate how the voltage and the current expression like this comes about in a transmission line. How is it even coming about? The voltages and currents that we are looking at is going to be time harmonic, meaning that whenever I have V as a function of Z and T, as a function of Z and T, I am removing the time dependence by having e power j omega t as the form. So real part of e power j omega t. So now all I have is only a function of space because my time dependence is taken off. Now I know that if I excite the transmission line at a point, it's not going to immediately reflect elsewhere. It's going to take some time for this to propagate through, meaning that there is a distributed effect. It's not an instantaneous lumped effect. It's a distributed effect. And how to see that is I can see this current I of Z to be flowing in on the upper current and flowing out in the lower conductor. V of Z is the potential between the two wires. I can go ahead and break this up into small sections, this transmission line into small sections. And in each section, all I see is a wire, essentially a wire here, right? And that wire, if I zoom in, it's going to have a certain resistance. And this wire is going to have a certain inductance. So there is going to be a resistance for this wire and it's going to have a certain inductance. Not only that, if I just take that section, it's like two conductors that are separated out, right? You know that two parallel plates, if they are separated, then there is a capacitance between them. There is a small capacitance between them, right? And not only that, if you were to fill it up with some kind of a dielectric material that has losses in it, if you were to fill it up with some dielectric material that has losses in it, then there can be a so-called leakage of current from this conductor to that conductor. There can be a current that is leaking through. And that is modeled by this G, C, L, R. So you got a so-called small section resistance, small section inductance, small section capacitance, and small section conductance, G. G is conductance, yeah. B is susceptance, yeah. G is conductance, like Y is equal to G plus JB, yeah. Y is the admittance, impedance, resistance, reactance. 1 over impedance is admittance, which is conductance and susceptance. So you got your RLCG. And this guy is going to repeat section after section. So it's going to repeat itself, right? So because of that, when you repeat that, what can you go ahead and describe this as? You can go ahead and describe each sections R1 and R1 for each sections. Though it is depending on the delta Z, the size of the section, since it's depending on delta Z, I can go ahead and write it in terms of R dash, L dash, G dash, and C dash. R dash, L dash, C dash, and G dash. Dash or prime, yeah? These are the per unit length parameters. When I multiply it by distance delta Z, I get the total resistance R, the total inductance L, the total conductance G, and the total capacitance C. So these are the per unit length parameters. And the units are going to be ohm per meter, Siemens per meter, Henry per meter, and farad per meter. Now this R, L, C, G are like the DNA of a transmission line. Yeah. So if we were to work out the Kirchhoff's voltage and current law, how the KVL and the KCL turn out to be, it will eventually end up getting a so-called differential equation. That means the change in voltage in space is dependent on current. The change in current with respect to space is dependent on voltage. So you go ahead and combine those two. When you eliminate current in them, you can go ahead and eliminate the current, because you can write this, differentiate it twice, substitute this I in here and eliminate I. Yeah, so that the entire expression is only in V. You will end up getting a second order differential equation. So how do you call it second order? Because it has d square over dz square. It's a second order differential equation in space. So it has this long expression. What you would want to define it as gamma square. We define it as gamma square. the current is eliminated. D square V over dz square is simply gamma square V. D square V over dz square is simply gamma square V. If you go ahead and solve this, you get the distribution of the voltage in the transmission line. So you can go ahead and solve for V of Z. Of course, to solve that, you need to know the wave equation, because this guy is something like a wave equation. It's just that there is no time dependence, and we call that Telegrapher's equation. Later, we will see what kind of solution, what can be V of Z be. In fact, it will have that sine and the cosine. It can be either the sine omega t plus beta z or sine omega t minus beta z kind of solution. So this gamma is what we call as propagation constant. It can be a complex number. The real part is attenuation constant. The imaginary part is the phase constant. So how is it related to the per unit length parameters? It's related through this expression here. Now, the important question that you really need to understand is this solution is, you don't have to solve it, but given that that solution is going to be of this form. If you're not convinced, the best way is take this V of Z, do the double derivative with respect to Z. Yeah, do the double derivative with respect to Z and substitute in back in here. You will see that it satisfies this guy. So this guy is indeed a solution. It is a solution of the Telegrapher's equation. Now, interestingly, this guy has two components. One is a forward traveling wave, which has a minus gamma Z, and the other one is a backward traveling wave, which has the plus gamma Z. So a forward traveling and a backward traveling waves. Similarly, you can go ahead and use that solution of V of Z to find your current I of Z, and that current would interestingly have V plus e power minus gamma Z minus e power V minus e power plus gamma Z. So this is the forward traveling one because of the minus gamma Z, and this is the backward traveling one. Very interestingly, this term that you see here is what is something like the ratio of voltage to current. Yeah, if you were to see it as a ratio of voltage to current, is 1 over Z naught. We define it to be 1 over Z naught. So there are two things you have defined, gamma and Z naught. What is gamma? What is Z naught? How are we going to use it? We will see it in the next slides.